Hi, everyone. My name is Will Crichton. I'm a postdoc at Brown with Sriram Krishnamurthy, and I'm currently doing research about what makes Rust difficult to learn. So this workshop is very relevant to me. And this talk is about my experience teaching Rust. And to mix up the format, instead of talking broadly about the course, I'm going to instead zoom in on a very specific homework problem called rebalance. And so during my PhD at Stanford, I taught the programming languages course. And as a part of that course, I taught students Rust. I actually wrote a whole Snapple paper about it if you're interested. But the high level bit is just that I was teaching Rust to fairly advanced students. And these were upper level undergraduates and grad students. And the question that prompted this talk is I was reflecting on what homework problems really tested a student's knowledge of Rust. Because I taught the PL course for 3 years, I tried out a bunch of different assignments and saw various levels of efficacy in terms of people could kind of guess and check their way through this one, or it seems like this one really required some mastery of the material to get through. And so the one problem that came to mind is the rebalance problem. So I'm going to explain the problem and the solution, and then I'll talk about why I think it's interesting. So in Rust, the problem is you have some particular data structure, like a binary tree with a leaf and then a node that has boxed children and some generic type T. And the rebalance problem is if you have a binary search tree, like the elements are ordered, then the goal is to lift the closest element on the larger subtree up to the root, and then rotate the former root as the root of the subtree, which is a little abstract. So if you look at it diagrammatically, with the example on the left here, that if you have, for instance, this left subtree is larger than this other subtree, then you would lift C here up to the root, and then you would rotate this tree DE down here. Or conversely, on this other example, if you have a big line A, B, C, D, then you would lift B up to the root, and then you would have A, B, C, D. So it sort of does a one-step rebalancing operation. And here's what a basic solution looks like. So the idea is you take a mutable reference to the tree, and then if it's not empty, you get the sizes of each subtree. And if there's imbalance, you have two cases, and we'll just look at one case. So like if the left subtree is larger than is too large, then you would say, okay, first detach the corresponding element that I want to move to the root with this helper function, right spine. Then you're going to replace that left subtree temporarily and detach it entirely. Then you're going to detach the whole tree itself out of self. And then finally, you're going to restore that new tree by creating a thing with the roots that you had just attached and store that back into self. And then the helper function, right spine, is also something that has to be designed as part of this assignment. So roughly speaking, it looks like this. In this case, this is left spine. So you traverse the tree until you find like the smallest or the largest node. Either there's no left child or no right child. And then once again, you have to do some kind of mem replace thing where you put in an element so it's not temporarily invalid. You take ownership of the thing, and then you pass that all the way up the recursive chain, at least when this is implemented as a recursive function rather than, say, an iterative function. And this is a somewhat standard data structures problem. Like, so there's a fair amount of references and boxes and such, and I didn't think it would be too bad. But then I went into office hours, and some students said they spent 8 hours trying to solve this problem before they came into office hours. And I was like, oh my God, what have I done? I'm killing these poor students. And the question was, why was this so challenging? So I thought in retrospect, it might be interesting to look back and boil that down to a few key aspects. And so first, this problem combines functional with imperative programming. So students who are unfamiliar with algebraic data types or like sort of inductive recursive styles of function design, option types, all of these things, I think they were going to be uncomfortable. Like in this particular PL course, we had studied OCaml before Rust to give people some functional background, but they had only seen it for a couple of weeks still. It wasn't like they were deep functional masters by the time they were writing this particular rebalance operation. But I think the more serious problem is in handling ownership. So, doing this operation in place requires a fair amount of care to satisfy the bar checker. Like you probably noticed there was a bunch of these mem replace calls, right? And this is because when you move objects around, you have to move objects around in this problem, but you also can't clone them because we don't allow T to be clonable. And so it's kind of like this, the scene from Indiana Jones. You're like, oh God, I gotta replace the idol, but make sure there's something there so the boulder trap doesn't fall down on top of me. I suspect that is how many students felt. And students and the problem is, right, students familiar with C++ might just like leave a null pointer there while they're doing their work and then come back and fill it in later. But in Rust, that's not really a valid option unless you sort of wrap everything in an option, which wasn't allowed by the representation ascribed by the problem. Another complication is that there were a ton of different pointer types involved. You have owned t's, immutable t's, mutable t's, boxed t's, mutable boxed t's, options of t's, and so on. And I think students really struggled to keep all of these straight, to know when a given variable had a given type. And this is made even worse by auto dereferencing semantics, of course, where when you like match on something, are you dereferencing it or not? When you put an ampersand or a star on it, what type are you going to get back? When you call a function, is that going to implicitly convert something? And so the combined fact of many of these concepts being mixed in, plus the compiler trying to hide as much of these conversions as possible, I think made it very difficult for students to have a clear conceptual model of what their code was actually doing at any point in time. What piece of data, were they pointing to the box or to the data itself, or what have you? And this was also pre-Rust Analyzer, so it was even trickier. And one particularly tricky bit that I think summarizes a lot of these challenges is that students had to design their type signatures for the helper functions. And oftentimes, if the students got the wrong type signature, then they would spend a long time fighting the borrow checker to implement a function that would just never type check. So here's an example. So these are 3 helper fragments from real student code, which did not end up passing any of the tests. And one common issue you can, so these are things that would, like when you saw left spine in the previous code, this is the sort of thing they were trying to implement. And the core issue in all of these functions is that they're trying to return a reference to something, usually a reference to like a value or a binary tree node or a box of a binary tree node or something that is nested deep within this tree. But that is fundamentally problematic in this instance because you need to consume ownership of the thing you're trying to lift up to the root. Otherwise, you're never going to be able to create a new tree out of it and insert it there. And so that means that once you've designed this API, like once you say, this is the function I'm going to try and implement, I think this is where students really struggled because they would spend hours attempting to implement a function that was never going to work in the first place. So either they would come up with a function that does type check but doesn't do what they want, or they would have a function that does what they want but wouldn't pass the borrow checker. And so, I think there's that kind of a combination of design and implementation that students, partially I think I just maybe didn't equip them fully in the course to do this. This was maybe just too challenging of a problem in some respects. But I think it also encapsulates one of the hardest parts of Rust is this co-design of thinking about all the ownership problems that are going to arise, using that to inform the design of your function, recognizing maybe when your function is incorrect, like at the type level, and having to fix that. This was just a particularly tricky thing, I think, for a lot of students. And so that's a sample of the challenges that students had solving this problem. And stepping up a level, I said that rebalance might be what I'm calling a paradigm problem, in that it's this sort of small, self-contained problem that requires students to understand many relevant concepts to correctly implement. So for instance, it's very hard to guess and check your way to a solution here. Like one thing I have seen in some of my Rust assignments is students will avoid gaining a mental model of ownership because they can often rely on the suggestions by the compiler to fix their basic mistakes. And then they just blindly copy in or cargo fix whatever the compiler says, and then it ends up working. But of course, that doesn't scale. And so once they run into a problem that has too big of a design space or an exploration space, they struggle. And it's important to have that kind of problem because, right, we don't want to just say, oh, always rely on the compiler. This touches on several challenging aspects of ownership, right? You have own values versus references versus boxes. You have lots of overlapping borrows to things. You have to carefully make sure you're never doing anything unsafe. This is all, along with algebraic data types, you have to understand the relationship between matches and references. So I think it's nice to have one problem that's relatively small, but captures many of these sorts of concerns. And then, broadly, like one application of this is this can serve as like a litmus test to say, does someone really grok the relevant parts of Rust? Like if you are able to solve rebalance, then maybe that means you understand Rust on some level, right? I don't know that for sure, but I think that would be an interesting kind of statement if you could say that with some rigor, some guarantee. By the way, just for the concerned amongst you, I did check. Copilot cannot solve this problem. It generates both ill-typed code and incorrect code, like it fails the tests and also does things that don't pass the type checker. So at the very least, if we think this is an important problem, I think it's safe to say, it's not a co-pilotable level of difficulty yet, and I'm sure that'll change in a year. Certainly, if a bunch of these solutions got published to the internet, then that would change. But for now, it didn't pass the co-pilot test. And so just to wrap up, I think paradigm problems are interesting because they help pin down specific learning challenges for a language like Rust. So rather than saying like ownership is hard in Rust, which we all kind of know, we can instead say something much more specific, like people cannot design the right type signature for a helper function when rebalancing a BSD. And obviously, that is not a general statement that captures everyone's difficulties learning ownership in Rust, but I think the idea is that it focuses our efforts. And so if we could make this problem really easy for someone, then probably that would be making it easy for a category of problems that all have this flavor, right? But it's much easier to focus your efforts on something very specific than to just say, my goal is, say, to make ownership in Rust easier. And for what it's worth, this has been a very successful strategy within the CS education research community. So for instance, there's this problem called rainfall that's a list processing problem that has literally been studied since the 1980s and has been a really interesting kind of paradigm problem. Usually it's used for planning, like how do students decompose a big problem into subproblems, especially when they involve lists and conditional checks. And there's a whole literature on this that's just used like literally as one simple problem in a variety of really fascinating ways. There's another really fun paper called The Mystery of B : equals parentheses B is equal to false. You can see the citation at the bottom of the slide. Basically they showed that in an AP CS exam from I think 1989 or something, there was like one problem that if students got it right, correctly predicted their performance significantly predicted a lot of their performance on the exam. So the idea being that I think there are definitely cases in history where there are small problems that if you can get them right, often indicate a much deeper understanding of the concepts at hand. And so, that's about it. I'll leave you all with a question for discussion, which is, have any of you designed or encountered paradigm problems in learning Rust, teaching Rust, just exploring Rust? Because I think if we could curate a collection of these problems as a community, that would be a great help for both the theory and practice of teaching Rust. All right, that's it. Thank you for listening. And I will pop open the chats. All right, I don't know. Oh, I see where the starts. All right, so we'll start with Bart's question. Did you provide pseudocode for the rebalance? How much was Rust versus just understanding how to rebalance the tree? So let me share the actual Chrome thing. So if I go to CS242, all this is online. We didn't give them significant pseudocode. I'm sure there was some algorithmic difficulty in understanding how to implement this, but I think we gave them enough examples that the challenge was not understanding the algorithm itself, but rather understanding the kind of rusty aspects of it. So the specific thing we gave them was this. We gave them a high-level operation. We gave them several examples of how it worked. We gave them a slightly more formal spec. And we even mentioned a little bit on some of the relevant functions like mem replace, some of the relevant concerns that they would need in order to solve this. I think actually this piece of text I probably added halfway through the assignment because so many students were struggling with it, or I maybe forgot to cover it in lecture or something like that, and it was very important to solving this problem. So that's the full set of text that we ended up including, and I'll leave this in the chat if you're interested. Okay. Are there paradigm problems for simpler language fragments that might be amenable to an intro course? I think it's a great question. I don't know off the top of my head. I will say this is something that I'm kind of exploring in my own research right now. We're trying to create like an ownership inventory that is a collection of relatively small problems that could test whether somebody understands different aspects of ownership. So I'll probably have a better answer to this question, me personally at least, soon. In a couple of weeks or a couple of months. Keep your eye out on my Twitter if you want to follow me. But I haven't, rebalance, I think rebalance just stuck out of my mind because it was particularly hard. There were just so many people that struggled with it. Like the entire course was struggling, and some people to the extreme, like the 8 hours thing was a real quote. So I don't know of simpler problems that I think exhibited that same, I don't say the same level of difficulty, but the same net need for conceptual understanding. But I'm sure they exist. We just haven't found them yet. Any thoughts on the advantages of HTTP style scaffolding? They handle some of the more complex syntax patterns, such as in-place changes and allocations. Yeah, I definitely think, the flip side of a tricky problem like this is, of course, how do we teach it, right? And I'm absolutely not going to say my course was the optimal way to teach Rust so as people would solve the rebalance problem, both because A, it wasn't a Rust specific course, so we were teaching Rust as one of a couple languages that were intended to demonstrate a variety of PL theory, and but I do think it is a very important question of like, how would we expect a student to go about scaffolding their process here? Like, what is the series of mental steps they need to go through to say, this is the high level problem, I'm going to break it down like this, I'm going to turn this into this type, I'm going to design a helper function this way. And I think maybe the HTTP style of like design recipes could be useful here to some extent. I don't know how much commonality there is in Rust code that you can have a really like general design recipe. I think it might be more just idioms than full templates. Like, if you're trying to do X, like you're trying to work on a thing, but you need to gain ownership of a thing, but you don't have ownership on that thing, use mem replace, for instance. This is actually something I pointed out also in an earlier paper I wrote called the usability of ownership, which is one of the big challenges with, I think, with ownership is that people have these like high level constructs of like, I need to work on this thing, and then they don't, or I need to take ownership of this thing and work on it. But then they don't really have the vocabulary, nor do they know the set of standard library primitives that are intended for kind of solving these sorts of issues. Like, another good example is like, I need two mutable pointers into disjoint indices into an array. And it just turns out there's like a function for that you just got to know. And if you don't know that function, you're not going to do this without unsafe, which we don't want to encourage students to do. So there's a whole separate subproblem of like establishing that library of idioms and getting students to have access to that library, to understand it, and to be able to search it, that I think is a really interesting open question I haven't seen much work on. Probably have time for maybe one more question, if anybody has a queue. And if not, that's fine. We'll head into the discussion and then see what arises.
Well, it'll be faster to just say instead of type.
Sure.
I have found that sort of, I don't want to say the size of the standard library is challenging. It's that there are such many things that need just the right unsafe at the right place to do it in a reasonably efficient manner that we just say, okay, put in the standard library. And I find in many other languages, we don't need as much of that. And so, we have lots of like, okay, well, let's implement this standard data structure because we can do it in the language with the garbage collector and options and et cetera, just as efficiently as, the compiler writer could. But Rust doesn't have that. So many of them. And so then the larger ecosystem sort of pushes you towards, well, just use the standard library. Don't make your own, tree-like data structure. Just use this, right? Just use hash set for everything, kind of thing. So it does make these problems a little bit more challenging because there's such a tendency to reach for the standard library.
That's a great observation. It speaks to, in a sense, like the whole Rust experiment, which is, does the theory of the bar checker scale to real world practice? And the answer is clearly yes to an extent, but it requires so much unsafe code in practice wrapped in these safe wrappers that someone carefully designed that like to then have a fundamental understanding of the language or to be able to build these constructs from first principles is quite challenging. So yeah, and I think just the major question then is, what does that mean for students, right? Like how do we resolve that tension? Does that mean changing the way we teach the language? Does it mean focusing less on data structures or on the implementation of data structures versus their usage? Do we just bite the bullet and teach people unsafe anyway, and then have them learn that fragment of the language, which also feels unsatisfactory since like I don't think the Rust book actually teaches unsafe. It's only in the Nomicon that you're going to find this kind of stuff, right? Very small amount. So yeah, a great point for discussion. And so we're at 11:30. We can move on. Thank you for pointing that out.
So if we're moving on, I actually had a comment on this, but didn't want to interject. So is this conversation time? Cool. Yeah. So one of the things that I was looking at in my paper is the tools that we're using in the how to design program space course is like, what are the strengths and weaknesses of the tools like Dr. Racket, for example. And one thing that was interesting to me was having the teach packs, because like each little language that you use for different lessons can have its own documentation that goes with it. And so probably not for like a junior level course, right? But if you're teaching like a really big intro course, I do think it's worth at least looking to the idea of, okay, what functions are actually needed in an intro language? Can I have a version, not the full standard library, but my mini standard library that I use for this course, and have them be able to load up in their editor a version of the documentation that's going to show them things that are relevant to their course, but not overwhelm them with everything.
That's a great idea. I would love to have something like that.